Hello everyone. So previously we are discussing separation axioms. Today we will discuss several more separation axioms and some important theorems. So Tychnoff theorem, another one is metrization theorem. So let us see what we have discussed. So separation means given a topological space, if a point given two point, if those 2 points can be separated from each other by any one of these open set, then it is called T0 property. And if both of these points can be separated by one open set, that is, a open set contains a point but not the other point. If those two types of things possible, then this is called T1 space. This is possible for every disjoint points. And if given any two distinct points, those 2 points can be separated by two disjoint open set U and V, then this is called T2 space. Now what is T3 space? T3 space is same as given a point and a closed set F, if those two can be separated by open sets like this. So there are two disjoint open set which contains one open set contains the point, another open set contains the closed set. If this is possible, then this is called T3 space. And what is T4 space? T4 space is more, the condition is more strong. So if two closed set F1 and F2 can be separated by open sets, disjoint open sets, then this is called T4 space. And T3 plus T1, those two properties are called, if a space satisfies T3 and T1 axiom, then this is called regular. And similarly, T4 plus T1 is called normal space. But those two notations are taken in Munch's book, but in most of the cases, T3 and normal both are same, and in many books, both T3 and normal both assumes T1 axiom. And another possibility is also there, that is T3 T1 means the same as this condition only. Okay, so it depends on different books. So those are some separation axioms. Now there is another separation axiom. This is called T3 and half. Okay. If there exists, so let X and F, X belongs to the space X, and if for all X belongs to X and a closed set F contained in X such that X does not belong to F, that is, those two are disjoint. If there exists a continuous function F from X to R such that F restricted at this singleton point is 0 and f restricted on the closed set f is 1. That is a point, there exists a function which separates those 2 points. So one point from the closed set. It means there exists a function. So this is codomain, this is domain. So this says there exists a function. Suppose this is the space. Okay. There exists a function whose value is 0 on the point, this is x, on the point the value is 0, and on the closed set f the value is 1. The value on the closed set is 1 and value on the point is 0. If this is possible, then this is called the space is called T3 and a half. This is possible for all disjoint point with a closed set. Then the space is said to be T3 and a half space. So as before regular normal, T3 and a half with T1, this is called completely regular space. Completely regular. Okay. Now we may expect a space. Note that these axioms T3 and half, this is analogous to T3 because here we are separating a closed set from a point by open sets. But in this case, this is stronger condition. Instead of separating by open set, our demand is to separate it by some function whose value is 0 at the point x0 and on the closed set f the value is 1. So similar kind of demand can be made for this T4, right? We may demand that there should exist a function f whose value is 0 on this f1 and its value is 1 on this closed set f2. So this condition, this new axiom is not needed because of this important lemma which is called Urisan lemma. So it says, so note that T3 and half, completely regular, this will imply regular. Why? Because if such kind of separation exists by a continuous map, so take f inverse, take a neighborhood of 0 which does not intersect 1. So take, for example, take this neighborhood minus half comma plus half. This is a neighborhood of 0 and does not intersect 1. Similarly, take f inverse half comma 3 by 2. So those two neighborhood does not intersect each other, those are open, and those two neighborhood contains 0 and 1 respectively. So their p image will contain x and f, and continuous inverse of an open set is open. So those are open set containing this x1, this point and the closed set respectively, and those are disjoint because pre-image of disjoint sets are disjoint. So from here it is clear that T3 and half will imply T3. Similarly, if we give the condition, that is there exists a continuous function f map x to r such that f, so again a and b are closed disjoint set. I am considering this. Okay. So So there exists a continuous function f such that the value of f on A is 0 and value of f on B is 1. So this new axiom is not needed. This will definitely imply this T4 axiom, but it is not clear that why T4 will imply this. So Urisohn lemma says T4 will imply this fact. Okay. Let X be a normal space. Then for all AB which are closed subsets, closed disjoint subset of X, there exists a function which separates these two closed sets. Okay. So Urisohn lemma implies this direction is also true. This is the important thing. So completely regular Urisohn lemma, those two are done. Now the remaining thing is its extension theorem and metrization theorem. Okay. Let X be a normal space and A be a closed subset. Subset, not subsets. It should be called subspace because we are considering topological space. Then any continuous map F from A to R extend to a continuous map instead of F, we denote it by F dash from X to R. So it means if we extension, what is the meaning of extension? Extension means if we restricted F dash over A, then we will get the same function. So we may think this F as a particular part of this function. We are just restricting the domain. This is the statement of this extension theorem. Now, Tychnoff theorem, very important theorem. Tychnoff is okay. Tychnoff theorem. So, product of finitely many compact topological space is compact. But to prove this is true for infinitely many compact set, this proof is difficult, and this was proved by Tychnoff. So the statement is let X alpha be compact space alpha where alpha belongs to a indexing set, then the product topological space is compact. So this is very important theorem. It says not only finitely many products but any arbitrary product, then it will be a compact topological space. And what is Urisohn materialization lemma? It says any regular and second countable space is metrizable. Okay. Every regular second. What is the meaning of second countable? A topological space which has a countable basis. That is the basis elements. If we count the basis element, it is countable. Every regular second countable space is metrizable. Now, the last is tone check compactification. So previously we have seen compactification. So given a topological space X, then its compactification means another topological space X hat or something. Suppose Y is another topological space. So Y contains the topological space X such that Y is compact Hausdorff and closure of X is Y. Then this Y is called compactification of the topological space X. Now stone check compactification is a particular kind of compactification which satisfies a universal property. Okay. Let X be a completely regular space then Y is said to be stone check compactification if it satisfies the following universal property. What is the property? The property is this: for any compact topological space K with a continuous map from X to K, there exists a map. The topological. So actually, stone check compactification is not only the space Y but this map X to this map, and this is actually abused. So this X to Y, this is called stone check. This Y is actually compactive. Y is the space, but compactification is the process. So this process is given by a function, probably denoted by some beta. Okay, this is actually called stone check compactification. So it satisfies the property given any compact Hausdorff space with given any compact Hausdorff space with a map A, there exists unique map from this Y to K such that the diagram commutes. That is, this Y actually extend this map, right? We are getting a map such that if we restrict this map over X, we'll get F. So this is the universal property. Then this is why is called stone-check compactification. A better notation is beta X. Beta X. This notation is actually used everywhere. So this beta X is called stone-check compactification. Okay. So this is our first question. We will solve some problems. Here, the first question says true-false question. Teach extension theorem implies Udison lemma. Is it true? So let us see. So what is Teach extension theorem? It says if we consider normal space, then a continuous map from X from a closed set A to R, this continuous map extend to X, right? There exists G such that so A is a subspace such that G restricted over A is same as F. So this is the Teach extension. So A is closed subspace of a normal space. X is normal, right? And this is closed subspace. This is the Teach extension theorem. So now what is Udison lemma? For Udison lemma, there are given two closed set. We need to separate those two closed set by a function, right? So let A comma B be two disjoint closed set of a normal space X. Then we may define this function. Define F from A union B to R. Okay. How can we define the function? F over A, that is F sends every point of A to 0 and F sends every point of B to 1. So this function is clearly continuous, right? Continuous because we may check explicitly F inverse of 0, this is A, and this A is actually F inverse means the image is this discrete space, right? So we need to check F inverse of open set is open. So note that F inverse of 0 is A, but A is open in this subspace topology, right? We are considering we are considering this topological space, and A containing this space is open, right? Because those two are disjoint. A and B are disjoint, so it must be open. Open in A union B. Right? So this becomes a continuous function. F inverse of the image is just this discrete. Instead of R, we may write this 0, 1 with discrete topology. But R is also fine. And F inverse 0 is A, F inverse 1 is B. That implies pre-image of open set is open. Hence F is continuous. Okay. Why A is open? Because A can be thought of as A disjoint union B minus B. So B is a closed set. If we remove a closed set, we are getting A. So this implies this is open. A is open in this topology, in this subspace topology. A may not be open in whole topological space, but A is open in A union B. Okay. Now, applying Urison lemma, applying Urison lemma, sorry, T's extension theorem. T's extension theorem says, so this is actually closed subspace of X. Note that A union B, this is closed subspace of X. Closed subspace because A, B both are closed. So we can apply Urison lemma, T's extension theorem. It says there exists a continuous function. So this is continuous. Previously it is continuous. Okay. Function G, which is extension of F, such that G restricted over this previous closed set, which is A. Okay. So now use G to separate those two closed sets. So G is a function. G is a continuous function from X to R, such that G over A is same as 0 because G is same as F if we restrict over. So this is same as F over A, which is 0, and G over B by the similar reason G over B is same as 1. So from here it is clear that therefore its extension. So this is actually this G gives the Urison lemma. Its extension is it will imply Urison lemma. So this is true. Which of the following separation axioms inherited to the subspaces? So suppose X is T1 space and A be a subspace of X. Will it imply A is also T1? So what is the meaning of T1? This is X and this is our A. Okay. So T1 means 2 points can be separated. So 1 point can be separated from another by an open set. Suppose X is T1 space. Now we want to prove A is also T1. So we will choose 2 points from this space A. Since X is T1, there exists some open set. Now we will use the property of X. There exists an open set such that it contains a point but not another point, right? There, let X comma Y belongs to A, and there, then this will imply X comma Y belongs to X also. By T1 property or T1 axiom, X and there exists open U such that X belongs to U and Y does not belong to U, right? Then take U intersection A. So this is open in A by the definition of subspace topology. So it is clear, since X is also an element of A, so X belongs to U intersection A, and Y does not belong to U, therefore Y also does not belong to U intersection A, right? So this property is satisfied by this A. So T1 property is inherited by its subspaces. Therefore T1 property is inherited by subspaces. So X is T1, that will imply A is T1. So T1 is okay. By the similar kind of reasoning, we can prove T2 is also okay. It is, if a topological space X is T2, its subspace will be also T2. Now what about regular? Regular means T1 plus T3. So T1 is already inherited by its subspaces. So we only need to check if T3 is, that is the another thing, that is separation of closed set from an open set. So for 3, see. So this is our space, this is a closed set F, this is 1 point X, okay, and that is actually a subspace of this topological space X. So we have assumed X is at X, or given X is normal, and let A be a subspace of X. Okay. So for X belongs to A and F containing X be a closed subset such that those two are disjoint, such that X does not belong to A. Okay. We need to find some open set which separates those two things, that is this point from this closed set. So we may use the property of X, because we know about X, we don't know about this A. We don't know about A, but we know about X. So we will use properties of X. So F is closed in A. Since F is closed in A, this is A. That implies F equal to, if we take closure of F, so closure means we are taking closure in this topological space X. Okay. So closure of F intersection with, because F is closed. So closure may lie outside. For example, instead of considering A, we may consider A like this. So closure may lie here, that is in the boundary also. But if we intersect with A, then we'll get F. Now X belongs to A. So this will imply X does not belongs to closure of F, right? Because if X belongs to A and X also belongs to closure of F, then this will imply X belongs to this intersection. But we have already assumed that X does not belongs to this F, right? So therefore it must be true X does not belongs to F. Now F bar is, this is a closed subspace of X, right? Sorry. We want to take a closed subspace of A because we are using, we are trying to prove A is normal. Okay, F is a closed subspace of A. So now F bar is closed subspace of X. Therefore, by, and X does not belong to F, by normality of X, there exists open U comma V, open subset U comma V of X, such that this X belongs to U and this closure of A belongs to containing V. Now restrict this UV over A. Okay, so take U intersection A and V intersection A, which are open in A, and X belongs to U intersection A. F bar containing V, therefore F will contain in V intersection A, because F is a subspace of F bar, so F contain in V and also F contain in A. Okay, therefore F contain in V intersection A. So those are two disjoint. U and V, though those two are disjoint open set. Hence this U will be disjoint. So from here it is clear that regular also, or regular property are also inherited to the subspaces. Sorry, inherited by this one. Yes, 2 is okay, inherited 2. Okay, now what about normality? So if, is it true that subspace of a normal space is normal? So in this case, there is some issue. Subspace of a normal space may not be normal. So one of the example will be like this: close 0, 1. Consider this close 0, 1. This is compact. So by Tychnoff theorem, we have already discussed, by Tychnoff theorem, arbitrary product, so close 0, 1 to the power r, this is compact, right? This is compact. By Tychnoff theorem, this is compact. Compact, which implies close 0, 1 to the power r is compact. But if we consider, so this is compact and also Hausdorff, because product of Hausdorff spaces are Hausdorff. So this is compact plus Hausdorff. And we know a compact Hausdorff space is normal, which implies normal. So 0, 1 to the power r is normal. This is compact Hausdorff. Therefore, their product is compact Hausdorff. Hence, it is normal, because compact Hausdorff imply normal. But if we consider this subspace, open 0, 1 to the power r, this is not normal, not a normal space. Okay. But in this case, the proof is very difficult. So instead of doing this, let me give an easier example. So let x equal to a, b, c, d. Consider this 4-point topological space where topology tau is generated by the subbases BD and CD. This is subbasis S generated then tau. What will be tau explicitly? MTX will be there. Now BD CD will be there. Their intersection should be there. So their intersection is D. So D is there. Now what is the remaining thing? Their union, BCD. So every possible operation, intersection union is done. So this is the topology. And consider the subspace Y. Y is BCD. Then tau, what is the subspace topology? Tau Y. So we need to take intersection of those elements with BCD. So MT is there. X intersection Y give me Y. BD intersection BCD is okay, which is again BD. Now BD intersection CD is D. BD intersection D is D and BD. Okay, so everything is done. This is the topology. Now note that what are the closed set in tau. So in this case, what are the closed set? Closed set of X. Closed set of X with respect to the topology tau. What are those closed sets? Those are complement. So complement of MT is X, MT, BD, that is AC, and CD, which is AB, D, which is ABC, and BCD, complement of BCD is A. So we note that those are actually disjoint. Sorry, those cannot be disjoint. For example, ACAB has common element A. All those spaces except non-empty, except this empty set, has a common element which is A. So there is no disjoint closed set. Hence, the separation axiom, that is normal property, normal axiom is vacuously. There is nothing, no closed set. We need to separate. Okay. But for Y, here there are some closed. Let us see what are the closed sets. Closed sets are, in this case, Y, empty, C, and B. So those two are disjoint closed set. C and BD. Sorry. What is the complement of D, which is BC? There is we are considering BCD. BCD is okay. D, CD, BD, and there should be CD actually. BCD is already Y. So let us see Y empty C. Complement of CD is B, and complement of D is BC. So we note that here this B and C are disjoint closed set. Closed set. Right? Those are disjoint closed sets. Now, so for two disjoint closed set, this is one closed set, this is another closed set. We need to have open set which separates those BC. But what are the open set which contains B and C? So B is contained in Y, but we cannot use Y because Y cannot separate. So B contained in BD, C contained in this CD. But those two are not disjoint, right? Both has the common element, but there are no open sets which separate these two closed. Therefore, y is not normal. So though initially we have started with a normal space, but its subspace may not be normal, right? Actually, there is some issue because for the definition of normal, T1 condition is actually assumed, but this space is not T1. So this counter example is not a true counter example because this counter example to the following counter to, so this subspace of T4 may not be T4, may not be T4. Okay, because this space is not actually T1. We can see that the collection of closed set, those close, for example, B and C, those singleton sets are not closed. But for T1 space, every singleton point, every singleton set should be closed. Okay. So this counter example shows subspace of a T4 space may not be T4, but this is okay. That subspace of um, for this normal condition, this counter example is okay. This counter example only works for this. Okay. A closed subspace of a normal space is normal. So previously we have seen a subspace of normal space may not be normal, but if we assume the closed hypothesis, will it be normal? So let us see. Let A containing X be a closed subspace. So A is closed and X is normal. Given X is normal, and we are assuming A be a closed subspace. Okay. Now we try to see if this is, if we take F1 and F2 instead of A, so I don't want to use this kind of notation, so let me denote it by 1. So here we'll take A and here we'll take B. So let A comma B containing Y be to disjoint. So this is a closed subspace of X. Disjoint closed subspace of 1. So that implies, so those are disjoint, that implies A is, those are actually closed subspace. So closed imply A is same as A closure intersection Y, and B is same as B closure intersection Y, right? But Y is also closed, and we know that closure is the smallest possible closed set uh, which contains A. So closure means minimal possible closed set which contains A. But this closed set also contains A, right? Y also contains A. Alternatively, let us see closure. What is the meaning of A closure? And one definition is A closure is take all closed sets and take its intersection. All closed set, so that containing A. So if we take y is also closed set, right? So if we try to define a closure, y will also be there in the intersection. So if we take intersection again, then this intersection will be absorbed, right? Since y is closed, a is same as a closure, because a closure intersection y is a. Okay, and similarly b closure is same as b. Now we may use this normal condition. Since x is normal, there exists open disjoint open set u comma v such that a contained in u and b contained in v. So restrict those open set over y, right? So take u intersection a, v intersection b. Those are v intersection u intersection y and v intersection y. Those are open in y, disjoint open, right? And this forms a separation. And a contained in u intersection y, b contained in v intersection. So we see that a contains in one open set, b contains in another open set. Those two are disjoint. Therefore, this is actually true. If this closed assumption is given, then this statement becomes true. A locally compact Hausdorff space is regular. Is it true or false? Let X, this is locally compact Hausdorff. We may denote it by LCH. Okay. Locally compact Hausdorff. So X is LCH space. Then will it imply X is regular? Take X hat, which is 1 point compactification of X. Then this X hat is 1 point. We are taking 1 point compactification, so this becomes compact and Hausdorff, right? X hat is compact or Hausdorff, but a compact Hausdorff space is always normal. Therefore, X hat is normal. But normal implies regular. Therefore, X hat is regular. Now, subspace of a regular space is regular. Subspace of a regular, we have just proved this fact. It's regular. Therefore, X is regular. Okay. So the same thing can be proved for completely regular. The same idea. Normal will imply completely regular, and subspace of a completely regular space is completely regular. This is how we can prove this fact. So this is again a true statement. Given a T1 space X, which of the following are true and which is false? X is normal space if and only if for all disjoint closed set a comma b of X, there exists a continuous function f such that f restricted over a is 0, f restricted over b is 1. So note that this is the statement of Udison lemma. And we know that normal will imply this fact by Udison lemma. Okay. So for 1, Udison lemma implies this direction, right? It is normal implies there exists this imply continuous function separate disjoint closed set. This is the what? This is the statement explicitly closed sets. Okay. Now for this direction actually it is very easy to prove. So let us prove this direction. Let f be a function let f map x to R such that f over this closed set is 0 and f over this closed set is 1. Right? Take the neighborhood half comma 3 by 2 minus half minus 1 comma half. Sorry, this is not open. So this is open neighborhood containing 0 and half comma 3 half comma 2. This is another open neighborhood containing 1. So 0 belongs to this. So those are neighborhood of 0, 1. Those are disjoint, right? Then f inverse of minus 1 comma half which is equal to u say and f inverse half comma 2 which is equal to phi say u comma p are disjoint and u contains a, p contains b respectively. Okay, so we are done. This is the definition of normality. Therefore, x is normal. So this is true for any closed sets, disjoint closed sets, a comma. Therefore, x is normal. So this direction is also. Again, we can use the same proof, same idea to prove this direction. Instead of a, we can choose the singleton point. Okay, this as a closed set, and the same thing can be proven. So for 2, this is same proof, but this direction is not true. There are some counter examples, but those are actually some non-trivial counter examples, so I don't want to discuss this. So this direction is okay, but the reverse is not. This is not true. That's why, sorry, this direction is okay because function means it is stronger. Separation by a function that will imply separation by open set, disjoint open set. So this direction is okay, but this regular will not imply existence of such kind of functions. So that's why these axioms, there is a new axiom. This is different from this regular condition. So this axioms is called completely regular axiom, and the space is called a space which satisfies this kind of axiom is called completely regular space. So one is okay, this is true, this is false. Now you can prove and true or false. Given a product of topological spaces, product X alpha, this is Hausdorff regular normal. Then so is X alphas respectively. So it says product is Hausdorff means its component is Hausdorff 2, and product is regular will imply components are regular too. So let us see if this is true or not. Given let me prove for any one of this. Given product of X alpha is Hausdorff. Okay, is Hausdorff. So to see this, to see X alpha is T2 or not. Okay, so how can we show something is Hausdorff? We will choose two point and try to separate it by open set. Let x comma y belongs to X alpha, and those are not same. Distinct point. So if we choose any such points, then we are trying to show X alpha is Hausdorff or not. So xy belongs to X alpha. So those are actually non-empty sets. So we may pick take and so denoted by X alpha y alpha. Take a point x comma y belongs to product of X alpha such that alpha component are X alpha comma y alpha respectively. Actually, this direction proofs becomes complicated. So let us try to prove using contradiction. Make it more easy. If possible, assume X alpha is not Hausdorff. Then what will happen? Then there exist two points x comma y belongs to X alpha. Let me denote it by X alpha y alpha. X alpha comma y alpha belongs to X alpha such that there is no any open sets containing u comma v containing x alpha open sets u comma v of x alpha containing x alpha y alpha respectively. So there is no open set which distinguishes those 2 points. That means if we choose any two open set which contains x alpha y alpha, they will intersect, right? Now take product of u alpha, okay, uh, actually let me denote it by a different variable u beta such that uh, u beta equal to u alpha when beta is same as alpha, and if beta is not same as alpha, take u beta to be same as x beta, okay. And similarly we choose v beta. Same, v beta is same as v alpha if beta equal to alpha, and if beta not equal to alpha. So we are just fixing those u v, right? Sorry, here I have written u, so let me denote it by u and v. So we have only fixed those two component u and v, and we have just taken product. So for example, if this is u, then we have taken u cross this kind of r, so this kind of strip, right? So if you take this, then product u beta and product v beta are not, sorry, so x alpha is not Hausdorff. We have assumed x alpha is not Hausdorff. That means if we choose 2 point from x alpha, there is no open set, disjoint open set separating those 2 points. I'm making some mistakes. Okay, I'll try this problem later. Okay. Product preserves Hausdorff property, regular property, regular axiom, normal axiom, all of the above. So those two are easy to check. Sorry, this is easy to check. Product of two Hausdorff space is Hausdorff, right? For example, suppose x and consider x and y. This fact actually this will be generalized to arbitrary product. So if we consider x, y both are Hausdorff, then product is Hausdorff. How can I prove? So consider 2 points x comma y. This is 1 point, and x to y to another point. Those two are different point. Okay, distinct point. Then one of the component will be distinct, right? So without loss of generality, those two are different. Those two are different. That will imply without loss of generality, we may assume the first component is distinct. But x is Hausdorff. First component is x. X is Hausdorff. This will imply there exists open u comma v disjoint open such that x1 belongs to u and x2 belongs to v. So x1 x2 can be separated by open sets u. Now take u cross y and v cross y. Those are open in x cross y, right? And those are disjoint, open and also disjoint, containing x1 y1 comma x2 y2 respectively. So from here it is clear that product of Hausdorff space is Hausdorff. So it is okay. Let x comma y be Hausdorff. Then the conclusion is those two distinct points can be separated by open sets. Then therefore x cross y is Hausdorff. Now what about regular? So for regular is also easy to see. For regularity, use this fact. So regular, we know regular if and only if this property holds. Is for x belongs to open U, there exists for all x comma u, where u is open with x belongs to u, there exists open V such that x belongs to V, which is containing V closure containing y u. Okay, so this is the equivalent property which is equivalent to regular condition. But if we use this property, then it is easy to see. If we assume x is regular, then x will satisfy this property, y will also satisfy this property. Therefore x cross y, that will also satisfy this kind of property. For any x comma y belongs to u cross v, now we'll take u closer cross v closer, right? Since this and we can also have another property y belongs to v dash containing, or instead of, let me denote by subscript v1 containing v1 closure containing u1. So just take the cross. So this will imply x comma y belongs to v cross v1 containing v1 cross v1 closure containing u1 cross u1 u cross u1. So from here it is clear that this will imply this x cross y satisfy this kind of property, and this will, because that is equivalent to regular axioms, therefore product of regular space is regular. So this is also okay. Use this fact. Okay. Now what about C? Product of normal spaces is normal. So C is not true actually. Okay. So what will be the counter example? One counter example is, consider R with lower limit topology. This is not true. Okay. Counter example is like this. RL. RL means R with lower limit topology. So RL is actually normal, because why this is true? Because RL is finer than usual topology, and usual topology is already normal. Usual topology, R with usual topology, this is coarser and RL is finer, right? Since this one is normal, therefore RL will be normal. But RL cross RL, if we consider this product topology, is not normal. How can you see this is not normal? So we note that if we consider x comma minus x, this kind of pair, x belongs to R, this is so if we draw the picture, it will look like this anti-diagonal. Sorry, this is diagonal. So we are taking this anti-diagonal line. Okay. So if we consider this subspace, note that this subspace becomes a discrete subspace of RL cross RL. Why? Because what are the open set in RL cross RL? It will look like this kind of rectangle, this kind of square, right? The above and right side, those are open, that's why dotted, and the lower and left side, that part are solid, because those are actually closed. Those points are there, but those boundary is not there. So from here, if we take intersection with this kind of thing, then those points becomes open sets, right? So this line, every point, if we consider this subspace topology, then this is actually discrete space. That is, every point is open here. So now if we consider A is another thing, same x comma minus x, but x belongs to Q. Then clearly A is closed, because delta is delta is discrete. Similarly, there is another subset we may consider delta minus A. Okay, those two are closed sets. The thing is that this is not the whole proof, but this is just a sketch. Um, there are two closed sets, delta A and delta minus A. Those are closed, and those cannot be separated by open set. This is the idea. But this proof is actually given in the Monk's book, and it is slightly complicated. So it is better to look at this. Okay, this is the main idea actually. Which of the following are compact subspace of close 0 1 to the power n? So close 0 1 to the power n, nothing is mentioned, means it is uh, the product is taken with respect to usual topology. Okay. So note that this is compact space. This is closed bounded subspace of real number, therefore it is compact. Now by Tychnoff theorem, close 0 1 to the power any arbitrary product. This is means product natural number many times is compact. But here some subspaces are given. N means those are actually sequence. So explicitly, if we try to write explicitly, it will look like close 0 1 cross close 0 1 cross this, and the points will look like so something. We can write the point as A1, A2, this kind of sequence, A3 dot dot, right? Those are the typical points. So this is written in a single notation, An. So first, if we consider this subspace A1 equal to A2, note that if we consider the option A, A1 equal to A2, then this is actually homeomorphic to again open close 0 1 to the power n, right? So explicitly, let me write the homeomorphism close 0 1 to the power n. There are some sequence like this A1, A2, A3. It maps to. It is similar to shifting, right? A1, A1, A2, A3. Just a minute. Okay, it is similar to the thing that is R. If we consider this kind of thing, R goes to R cross R. Okay, then sorry. we are considering this subspace A. We try to prove A is homeomorphic to this. So an element of A will look like first two elements are same. So instead of writing A1, A2, we may write A. So A1, sorry, A comma A, then A3, A4 like this. So we just cancel the first element A comma A3, A4 like this. This is, recall, this is similar to shifting. That is one point. This first point is just removed. Okay. So this A, and if in the reverse direction, G maps this close 0 1 to the power n to A given by G of A1, A2, A3 like this is same as, just repeat the first element A1, A1, then A2, A3. So those two are inverse of each other, right? Therefore, A is homeomorphic to close 0 1 to the power n. There are several things need to be checked. That is, f, g, those two are continuous function. Inverse, checking inverse is easy, but checking continuity is tricky, but not very difficult. It can be easily checked because we know that product basis open sets, basic open sets, it will look like product of U alpha, and it is very easy to check that f inverse of this kind of thing is open. Okay. So from here it is clear A is same as close 0 1 to the power. That is, A is homeomorphic to this close 0 1 to the power n. Hence, which is compact. It is earlier proven that close 0 1 to the power n is compact. Therefore, A is compact. But there is another way to see. Another way, alternatively, A containing close 0 1 to the power n. This is actually a closed subspace. Closed subspace, right? By definition, A is a subspace of close 0 1 to the power n. And this is closed. Why? Because of this condition. We can easily prove that complement of A is open. It is similar to diagonal line. If we consider only two component, it is this is actually A. But here there are multiple dimensions. So we need to draw Z axis, W axis, etc. Infinitely many dimensions. But this is the point. So the proof is same as saying that this diagonal is closed. Okay. We can prove how do we prove the diagonal is closed? We just prove the complement is open. If we take any element, then there exists open set which belongs to the complement. This is how we can show that A is closed. So A is closed subspace of a compact space, and this is actually so. And we know every closed subspace of a compact space is compact. Closed subspace of a compact space, hence A is compact. This is another way to see compact, if A is compact or not. Now what about B? B is similar kind of thing. B is also, we can show that B, this set is homeomorphic to this close 0 1 to the power n, and another way is that this set is same as This set is also a compact set, compact space, closed subspace of a compact. This kind of condition is, so for B it is, let me denote it by B, n such that A1 first entry is 0. So B, let us consider this function pi 1 from this closed 0 1 to the power n to r, given by pi 1 of a component, pi 1 of xn is same as first component. So B is same as pi 1 inverse. This is continuous. Okay, very easy to check. Pi 1 inverse of this singleton set 0 is actually B, and 0 is closed in R, right? Therefore B will be the preimage of closed set under continuous map is closed. This is closed in closed 0 1 to the power. Therefore B is compact, because a closed subspace of a compact space is compact. So B is compact. Now what about C? N such that the first component is positive. For C, N such that A1 is greater than 0. C is same as the same pi 1 inverse open 0 infinity, which is open. Therefore this becomes open. Okay. So C is open, therefore C cannot be closed. Otherwise, because this is non-trivial set, not the whole set, not the empty set, C cannot be simultaneously open and closed. Otherwise, this space will become disconnected. So 0 1 infinity to the power n is connected. This will imply C cannot be closed, because C is both open and closed. Non-empty set, C is non-empty set which is both open and closed. That will partition this closed 0 1 to the power n into two parts. One is C, another is C complement. Both are open, non-trivial open set. That will contradict to the fact this is connected, right? Therefore, C is not compact. Why? Because C, because compact subspace of a Hausdorff space is closed. Close 0 1 to the power n is also Hausdorff, right? Close 0 1 to the power n is Hausdorff, and C is a subspace of this Hausdorff space. So C is closed. C should be closed, which is not true, right? Therefore C is not compact. So similarly, we can prove D. D is the same kind of thing. Instead of this phi 1, we should consider two functions. For D, consider f map close 0 1 to the power n to R given by f of an equal to a1 minus a2. Then this set, let me denote it by D, a1 is greater than a2, that means a1 minus a2 is greater than 0. So this D set is same as F inverse open 0 into. This is continuous. The proof is easy. So D is same as this, which is open, and again the same reasoning will imply D is not compact. Sorry, those are not correct actually, those are false. So first two are okay. Normal subspace of normal, those two are false. This is actually true. Why the proof is not working? The proof is actually easy. The idea is, so I don't know why this is not working, but the idea is clear that if one component is not open, then that will imply that, sorry, if one component is not housed out, so if the, there is no such separation, then that will imply we can construct 2 points and that cannot be separated in this product. This is the idea. Okay, so this is true. I don't know why this proof is not working, but you can write and check. This proof is not very hard. It is very easy. I don't know what is the mistake I am making. Sorry about this. Which of the following are embedding? So, embedding, what is the definition of embedding? Embedding means it is a continuous map f from x to y such that x is homeomorphic to fx by the same map. That is, image set fx with respect to this subspace topology of y. This is homeomorphic to x. Okay, homeomorphic by f. If this is the case, then f is called embedding. So, by the definition, it should be clear that f is injective. Otherwise, this kind of homeomorphism will not exist, because we need to find a map in the reverse direction from fx to x, such that f compose g and g compose f is identity. But g compose f is identity, that will imply f is injective. F may not be onto, because we are not considering whole y, we are only considering fx, the image set. Okay. So observe f is injective. Embedding means it is injective. So if we consider the first function f from r to r2 given by ft equal to a to the power 2 pi I t, know that f0 is same as 1, f1 is also 1. So 2 point goes to the same element. Sorry, e to the power 2 pi I means 1 in complex plane, but it is actually 1 comma 0. Okay. cos 2 pi 0, which is 1, cos sin 2 pi 0 is 0. So this is, therefore, for A, this is F is not injective. Therefore, it is A is not embedded. What about B? For B, all those maps are continuous because sine, cos, those kind of function makes those are continuous functions, and we are taking component wise. By product definition of product topology, this is continuous. But we also need to see X is homeomorphic to Fx. So one way to check, another thing, interesting thing, if F is injective plus open or closed map, then F is embedded. This is easy to check. Okay. So in this case, for if we take Ft equal to e to the power 2 pi it, this actually becomes open map. So it is just wrapping here like this, right? Take any open set, it maps to some open segment of the circle. Okay. So F is open and it is also injective plus injective, and continuous is already clear. Continuous. Therefore, F is embedded. Now, what about C? F maps closed 0, 1 to R. So it is like this. So the image will look like this. So this is, we will start from this. At this point, it is 1, 0, this value. Then this is the value at 1, 4, then half, 3 quarter. Then it will end at this point. So note that all those points are there. Each point of the circle is there. But the problem is, for we need to see that if X is homeomorphic to Fx or not. This is the point we need to see. So if we consider this neighborhood, a neighborhood of 0, for example, close 0, 1, 4, this is a neighborhood of 0, open neighborhood of 0, right? But if we consider F0, then F0, F1 by 4, this will be the image of this F of 0, 1 by 4. This is same as this segment, right? This is actually this segment. This point is there, 1, 0 is there, but this point is not there. This 1 quarter part. Okay. This is not open. This is not open. Why? Because this point is there. Not open in R, not in R2. We are considering the space. The definition is we need to consider this Fx. So this is not open in F of closed 0, 1. That is the image in the circle. Closed 0, 1. Right. may not, I should not write S1 because S1 represents a space, topological space. But geometrically it looks like a circle, but the problem is this this is not open in this space fx, right? This is not open because this fx inherits from the topology inherited from y, but in y there is no such open set. We cannot write this set as some open set intersection. For example, if we take this kind of open set, then note that this point should not be there because R2 intersection with this, which will give some arc, right? Some kind of arc like this. It will not contain any end point. So that is the problem. Right? So F is not an embedding. Not an embedding. So C is not embedding. D is okay. Okay. So it is 7:57. There are few questions. For example, this is a question from uh, the proofs is similar to the stone check compactification. So let us solve this question. There are several questions, but let me solve this. So X is the open interval 0, 1. Find a compact set Y such that closure of X is Y and the function f1, f2, which are given by t and sine 1 by t, extend continuously to y. Okay, how do we prove? How do we find the compactification? So there are lots of compactification, but we are trying to find a compactification such that by those compactification, those functions extends to y. That is, there are some map x from f from x to r. I want to find a compactification y such that this f extends to this y, right? Extend over y. This is over y. So answer. Consider this function f from x to r. Okay, defined by f t equal to t comma sine 1 by t. And so this will be an embedding. Now consider the image fx. Okay. Then take y equal to closure of fx. So we are getting pictorially this is same as this topological sine curve, and we are taking closure of this. Closure means it will contain this endpoint and this point on y-axis. So if we take this, then this is closed bounded subset of R2, hence it is compact because closed plus bounded in R2 in Euclidean space, hence it is compact. So we already have a compactification x to y. Though x is not a subspace of y, but it is clear that x is homeomorphic to fx, right? So instead of working with x, we can work with fx. So we get a compactification. So F is the compactification. And we already have a map from X to R2. This is F. Right? X to R, those are F1 and F2. So take the projection. For example, take the projection on x-axis. This will give this, that is, if we take the projection pi1, then I will recover the map T, Ft equal to T, the first component, right? So if we take the projection from this y to r, pi1 and pi2, I will recover Fi. Okay. So those pi1, pi2, so F1 and F2, those are extended to this pi1 and pi2, right? So we get extension of F1, F2. Therefore, pi I are extensions of F1. This is the whole thing. So let me stop here. Thank you for this essentials of topology classes.